let's try to compute the method in C. So you will have a polynomial transfer functions like this, right? And then okay, let me clear this one first. Okay, CLC. Okay, notice that I clear the command window, but I don't clear the workspace because the workspace still contain the previously input transfer function, right? So now GS3, okay, that's GS3, all right? We want to do this one. Okay, first, because the systems contains numerator and denominator, so we have to first define what is the numerator of the systems. Okay, just put nums equals to, put in bracket the coefficient of the numerator, which is 100. Okay, express it. Okay, and then denominator, just put den, put a square brackets. Okay, input the coefficients of that denominator, which is s squared, is just consider 1, and then space in between 3 and then 5, and then put bracket and suppress. Okay, notice that if you have a negative sign here, right, let's say for example s squared plus 3s minus 5, that 5 here has to be minus, right? So that is a coefficient, the sign of the coefficient has to be there. Okay, now we already define numerator equal to 100, denominator is 1, 3, 5. So you follow this one. If let's say our system is GS3, let's say GS3, right? So we have to make it as a transfer functions. We need to write like this, bracket. So we can write numerator, right? Numerator, and then comma, denominator, right? And then that. Okay, now this command will transform this numerator and denominator into a transfer function like this. So it seems correct, right? So this is our transfer functions. Then we see the same thing in the Matlab. So that means we are entered correctly. Okay, the other methods we can use this method, right? This is a zero poles and gain methods, because within the transfer function we can split, because I think this one will be covered in the next chapter. I'll show you here. Okay, this 10 is a gain, this is a pole, this is zeros, these two are poles. Okay, poles and zero. So knowing that, we can actually simply split this into 3 ZPK 0 poles gain. So from that transfer function, we know that our zero is minus 1 as, okay, there's a 0, the roots of that 0. Okay, the numerator is 1. Okay, now we can compute GS4 equals to ZPK, and use that command ZPK, which is 0 poles and gain, right? Okay, and then what is a 0? It's minus 1. Okay, and then separate by comma, and then poles, that is the number denominator, which is the coefficient of denominator is s equal to minus 5 and s equal to minus 2. So just enter it, put in the bracket, minus 5 and minus 2, close bracket, and then separated by comma. Gain is 10. Okay, all right, gain is 10. Okay, now we enter this. Right now we get the same thing, right? So there are, different ways to enter it, but you can actually choose the best way, the easiest way for you, right? Okay, now when we have these the transfer functions created as an object into the Matlab workspace, we can run the analysis of the systems, right? So okay, now I want to clear this space first. Okay, clear. So I don't want to clear the workspace. I just clear the command windows. I don't want to clear the workspace, because if I were to clear that, I have to re-enter again the transfer function, right? So we can use that transfer function to do some analysis on it. Okay, now the next one is this is a state space we haven't covered yet. So okay, let's go to number 4. Okay, how to obtain system parameters from the transfer function that we have entered, right? So if let's say we want to find the roots or zeros or poles on the transfer function, let's say we have GS1, right? GS1, we just type that, we call back that object GS1, then this is our transfer functions. We know that by looking at it, we know that the roots or the root of the denominator of the transfer function is s equal to -1, s equal to -2, right? S equal to -1 and s equal to -2. So we want to run this command to see what is the value of that, whether it's correct or not. So we can run pz map, right, system. No, in this case we just put gs1. Okay, it shows you the locations of the poles, right? So first one is -1, and then this is -2, so which is correct, right? So you can see that if you have a higher order system, you can simply run this, so you don't have to use calculator to calculate, right? Okay, let's say just close this first. Okay, I want to create higher order systems just to see how easy it is. High order, right? High order. I just put high order equal to 1 over just the bracket. Maybe s to the power of 3 plus 3 s to the power of 2 plus s plus 5. Okay, so this is a transformation. I have higher order systems, a third order system. It is difficult for us to find the the locations of the roots. Okay, we can simply run that command pz map, right, and then high order. Okay, then you can see that okay, there are 2 poles on the right hand side, which is the system is not stable in this case, right? Because you see that this is 0, so there are positive roots on the right, and then this is 1 on the left side, because they have 3 roots. So as easy as that, you can run the command, you can see that. Okay, so this is just to plot that the roots on the S-plane. You run this command. If you want to see it on the screen, you just run this. Okay, pz poles and 0 means that equals to pz map. Okay, same thing. You can put the systems gs1, right? Enter. So it gives you straight over here. You don't show you on the screens. Just poles -2, -1, 0, nothing. So because 0 is the roots of the numerator, so we don't have that, right? Okay. This is for state space. Skip that. So how do we find these time domain response analysis that we learned before using calculation methods like TR, TS, TP, overshoot, and so we can actually simply run a command, and then we get all the values. For example, in this example, right? So we can use the command damp, D-A-M-P, it gives you the zeta and natural frequencies. Okay, so we run on the GS1. Okay, so give you these the poles, means the root just now, the -1 and -2. There's a damping is 1, frequencies is 1 and 2 for that, and then time constant is 1, 5, right? So it gives you all these values. So this is in a first order system, because if we treat this separately, so we're going to have two different time constants, 1 and 5, and then the frequency will have different frequencies, because we treat them as a two separate first order systems, the second order, right? Okay, that's about damp systems, damp's command. So if we were to test to check the response of the system, we can simply run step system. That means we we want to see the step response that systems. We just type step GS1. Okay, all right, you see that straight away. That's the response here, right? So that is the response of that systems, right? You can see the times here, and then the amplitude here, and then there is a steady state values. Okay, and then if you click that, you see that, okay, that's the times and also the amplitude, but it is very difficult for us to determine where is the settling time, where is the rise time, and so on, right? So if we were to we can do like this, right? It's difficult to see. Right now we can use the command, the step info command, to see the value straight away without having to see the response, right? So we can just tap info, okay, and then run GS1. Okay, enter. So give you all these values. In fact, if we run the command just now, the step GS1, right? So it is behind this. Okay, see this one, all right? There's a settling time, say somewhere here, right? So we just correct. Okay, the rise times overshoot, of course, is 0. There's no overshoot, right? So we can see straight away from here, or alternatively we can use an apps. Okay, close this first. You see that on top of the Matlab program there is a home, plot, and apps, right? If you click these apps, you will see that there's a apps called linear system analyzer, right? There are a lot of apps there. Click this. Yeah. Okay. Under the control system design and analysis, there is a program, apps called linear system analyzer. Click that system analyzer. Okay. So you will have this response page, but we don't have anything on the graph, on the response there. What we have to do, we have to import, because it is a step response, import. So there you see the workspace there. You need to identify which transfer function you want to see the response. So you want to see the GS1, so you just click this from the workspace, or you can click from the map file if you have one. So right now we have all the transfer function we save in the workspace, right? So I think it's a good idea to create the transfer function in the M file, so that you don't lose it when you close the Matlab. Next time you can actually recall it. This one, when you close it, everything's gone, so you have to create one by one again. So in this case we have GS1 here. Okay, we call it the same thing, right? It's a step response. Then we can have the response, and then we can choose from the menu here, right hand clicks on the graph, you can choose the step or impulse. Okay, and then okay, pole 0, that is the remember we run before, right? So we can click here, impulse, that's the response for impulse input, step. Okay, now this is our step input. How are we going to see these parameters, right? These parameters on this graph. So click here, you can go to characteristics, right? You see that you click any of this, the settling time. So it gives you that the settling time point, which is a 4.6 second. And then if you want to see the rise times here, so it is 2.59, maybe steady state. So this is steady state, values is 0.5, then peak response is at times. Okay, all these values here will be clearly displayed on the response, so you will have a better a clear picture how actually the response and relates to that parameter that you obtain. Right, so so you can try many examples in the books, and you can see it, you can verify your calculation, although you know calculation might probably give you different, slightly different values, but because of you know the calculation is approximation, it's not accurate. So this one is the accurate one. Okay, so I'll probably close this one. Okay. All right. Now, if you want to, let's say this step command is just a 1/s. If you want to, you know, multiply 2/s is double the step input. Let's say 2/s. So you still run the same command step, but you need to multiply by, let's say, 2/s. 2 by multiply gs1. That is equals to the step input 2/s. All right. I just enter it. 2 multiply gs1. Sorry, gs1. Okay, you see, previously the input is double, the steady state is 0.5. Now we increase the step inputs to double the step input, then we get the output is equal to 1, right? So we can plot multiple response on the same graph by running a command hold on. That means hold on. That means the next time if you want to run this one, we're gonna see, right? You see, there's the same on the same graph. Okay, just try different, maybe 3 times gs1. Okay, you will have a 3 graph the screen, right? Okay, what we want to see here is that same things as we learn in first order systems. You see, the input doesn't change the characteristic of the systems. So if it's the settling time is 4 point something, it remains 4 point something even though the input change, right? So meaning that the parameter don't change if you change the input, right? So it belongs to that transfer function or that system itself that represent the physical systems, right? So that's why if we want to change that parameters, we need to build a controller later on. So as of now, we need to understand that whatever we do on the input, we don't change the parameter of the second order systems. And the same thing for first order system, all right? So you can try another example here. Okay, I think that's all for this the time linear analysis, right? Time domain analysis. So we can as long as we can compute the transfer function into the Matlab and then run a few commands, then you have all the information at hand, right? So right now you can try to create, go back to home, scripts, then you can run to, let's say, show you. Okay, we need to, let's say, we need to write s equals to tf, because next round we don't have to run the program on the command window, so let the Matlab recall from the file straight away. All right. Okay, I want to suppress it, and then I want to input one first. My transfer functions is my gs1 says system, let's say system1 equals to 1 over s to the power of 2 plus 1. I want to create over them under them systems as plus 1. Okay, and suppress it. Okay, now I want to see if what is the values of what is the response. I need to put step input. Okay, let's say okay. Okay, I want to run the step command. Yeah. Okay, let's probably just comment the line first. Okay, step input 1 over s. Okay, so steps system1. Okay, and then I want to see the step info on the screen. Step info, right? Sys1, and then probably, yeah, that's all. That's the end. Okay, I want to see these two. Right, I want to see the response. Okay, let me see. Probably I want to plot another graph on the screen, which present the impulse input, impulse system1. Okay, hold on, and then I want to see this place. Okay, now I save this. Okay, save this, close, save. Test program 2. Test program 2. And file save. Okay, save. Now I have this one, right? So I can now clear all this one. I'll let the test. I want to have these variables and object from the test programs to be displayed on the workspace. Now I want to clear this. So I clear the workspace here. Okay, gone. And then I want to clear this command windows, CLC. It's gone. Right, now I want to run this. Okay, I can double click this test program 2. Okay, you can as I show you before, you can write the names of the file and then enter here, it run the program. Alternatively, I can open this file, double click this file, I can run this. Okay, click the run button. Okay, you see that impulse system1. So I got the wrong syntax spelling here. Okay, but you see there's a response for that. I know that this is under them system. Okay, I'll do it again. I just maybe change, do some correction. Impulse here, I save it. Okay, and then I run it. There you go. You see that is the response for this command, step systems, and then this is impulse systems. Then at the same time, you can see the step info, what is the value on the screen here, right? So you see, regardless of the inputs, impulse of steps, the value remain the same, right? That's because that value is belong to the systems. All right. Okay, I think hopefully you understand this. because I will provide you some example, and then you need to do some, um, tests, and probably you get better understanding about how to do this. All right. Okay. Thank you very much for your attention.